Hi, my name is Zerina, and I'm a PhD student at the University of Washington. Today I'm going to be presenting our work called Glaze, which is all about how we can overlay data on top of occupied spectrum. So we're all aware of the vast amount of IoT deployments over recent years, which are continuing to rapidly increase. We see them in our homes, cities, even large industries such as agriculture. And while they provide huge benefits, there are also a few drawbacks, specifically around the cost and maintenance of IoT systems. They can get expensive when we consider the cost of base station hardware and antennas, not to mention tower space and management that quickly bring up the cost. The other challenge is that most IoT devices use batteries and require routine maintenance. So the question we ask is, can we utilize existing infrastructure and minimize battery usage to connect IoT devices? Ambient backscatter is a relatively new technology and is promising because it leverages existing wireless signals, it's low power, and can enable both peer-to-peer and uplink communication. In fact, it's so low power that you could even have sensor nodes that are completely batteryless. However, to have an end-to-end IoT system, we need both uplink and downlink communication. Glaze helps bridge the gap by providing a new solution to enable low-power downlink communication for ambient backscatter systems. Since TV transmissions already exist, they can be used to carry downlink data. Similarly, FM transmissions or Wi-Fi could be used the same. But we don't want to require power-consuming Wi-Fi or FM receivers at the endpoint devices. To transmit additional data using Wi-Fi signals, for example, without requiring a Wi-Fi receiver at the endpoint device, we overlay low-rate data transmissions on top of the signals. The endpoint device then only needs a simple low-power radio to decode the low-rate Glaze downlink message. To avoid making changes to the transmitting radio hardware or firmware, we propose connecting a Glaze module to the antenna port of the wireless radios to overlay data on top of the RF signal. A Glaze module can connect to the antenna port of a Wi-Fi access point to encode downlink data transmissions for ambient backscatter devices, while Wi-Fi packets are still being transmitted and received by legacy receivers. But enabling this is non-trivial. We need to ensure that the data we overlay does not cause channel degradation. It needs to operate at low power. And lastly, how will we overlay data on signals that use packetized protocols? For example, Wi-Fi, which sends data in bursts. We designed the Glaze module to address these challenges, which has 4 key components. First, a signal detector to monitor for incoming transmissions, a parameter optimizer to optimize encoding parameters based on signal type and channel conditions, a traffic predictor that predicts incoming bursts of traffic for Wi-Fi signals using a 2-state Markov model, and lastly, the Glaze embedder, used to overlay data on top of the RF signals by introducing small perturbations in the form of attenuation. A 0-bit is encoded by introducing attenuation, and a 1-bit is encoded by making no change at all. So how do we receive the data encoded by the Glaze module at low power? We designed a low-power Glaze receiver that has 3 key components: a completely passive envelope detector to get the baseband signal, a RC circuit to compute a dynamic threshold based on the input signal rather than using a more power-consuming ADC, and lastly, a low-power microprocessing unit to decode the data. Here we can see the prototype implementations of the Glaze module and receiver, which we use to evaluate the Glaze system for 3 different signals: TV, FM, and Wi-Fi. The Glaze module prototype uses off-the-shelf components, while the Glaze receiver is a custom-built PCB. Next, I'll go over some results, but due to time, we'll only cover a few things. The first thing we evaluate is the impact towards the original signals. To perform this evaluation, we look at a couple different metrics depending on the signal. For example, the perceptual evaluation of speech quality for FM, which is what I'm going to show you today. Here's an example evaluating FM audio quality after data embedding. We look at the PESQ with respect to RSSI for demodulated FM audio after Glaze embedding compared to a baseline that has no embedding. The PESQ can range from 0 to 4, and a score greater than 1 is considered sufficient for human hearing. We perform this evaluation by recording an FM broadcast signal using a software-defined radio. The signal was then retransmitted with the Glaze module connected to the antenna port of the SDR to embed data. We can see that the PESQ remains very high for all amounts of attenuation and starts to drop off around -70 to -75 dBm, similar to the baseline signal. The impact Glaze has on TV and Wi-Fi is similar, and these results can be found in the paper. The final result I will show you is the performance of Glaze itself. We evaluate the bit error rate with respect to distance in meters for Wi-Fi, TV, and FM signals for a bit rate of 10 kilobits per second. A SDR is used to transmit each signal with a transmit power of 20 dB. Wi-Fi was transmitted at 2.4 GHz, and it was impractical to emulate FM and TV broadcast towers, so we transmitted at 915 for those cases. The Glaze module is connected to the antenna port of the SDR to embed data, and the Glaze receiver is used to decode. We can see that Wi-Fi has a range limitation of 4 meters, while TV and FM work up to 10 meters. This makes sense, and fundamentally, Wi-Fi will have a shorter communication range in comparison to FM and TV just by considering the carrier frequency. We would also expect that in a real-life scenario, the communication range for broadcast signals like TV or FM would be significantly larger. An estimated communication range for FM and TV broadcast scenarios would be 125 kilometers and 75 kilometers respectively. So to conclude, I present a high-level overview of the Glaze system, which can be used to enable a new channel for downlink communication. And I definitely recommend taking a look at the paper to get more details on our system. Thank you.